So let's first recap a little bit of what we have been talking about in the last lecture. So since the last lecture, we have started talking about reinforcement learning with function approximation. So we start with the simplest case on the linear function approximation. So we say for the linear function approximation, the most important thing is we can make sure the value is linear. So we resort to first a sufficient condition, which will guarantee the value is always linear. That is called linear MDP. So in the linear MDP is an MDP with all the similar elements. We have a state set, action set, transition, reward, and horizon. But the most important thing is in the linear MDP, the reward is linear. That for every step, the reward of state action pair SA is equal to the inner product of some known feature map, phi SA, inner product with some unknown parameter, theta h. And also transition is also linear, where we see again this transition probability going to the next states, going to the next set in general, like if it's continuous, and the probability of reaching some set starting from SA is equal to again some linear inner product of phi SA, inner product with the measure mu. And also in the very end of last lecture, we're talking about we want to do essentially the value iteration for this like linear function approximation. So the algorithm we talk about is so-called least squares value iteration. So because we're doing function approximation right now, so instead of exactly solving a Bellman equation, now we're just solving the value, linear value, which minimize the square loss. So we say we will parameterize QH as something like a phi SA inner product with WH, where this WH, we will solve WH as a argmin of some problem where this is like least square summation I from 1 to n if we have n different data. W transpose phi Si Ai subtract I subtract VH plus 1 hat Si prime. So that is if we have collected a lot of data tuple that is in the form of Si, Ai, Ri, Si prime. This is like starting from the current state action pair, what is the reward we're going to get, and what is next state we're going to transition to. In the linear function approximation scenario, we will, instead of directly solving the Bellman equation, we find the linear value which minimizes this square loss. So today we'll talk more about the property of this algorithm. So you can think in this is like a generalization of the tabular setting. So we will see this more. So first, let's define this square loss as JW. Let's first solve for this least square. So like what is the answer for this least square? So in order to find the minimizer, we first make the gradient equal to 0. This basically, we will take a derivative over this objective function. And this implies summation I from 1 to n, phi I. Let's call this thing as phi I to make it simple. So we have phi transpose W minus I minus VH plus 1 hat Si prime. This thing equal to 0. So this just implies you can think this is you can make this thing as a matrix or lambda. Let's denote lambda equal to summation I from 1 to n phi I transpose. We can directly solve this WH hat. The solution of W is equal to lambda inverse times the summation I from 1 to n phi I Ri plus VH plus 1 hat Si prime. I'm directly telling you the answer, but it's very simple. It's like a standard solution for the least square. I just want to also comment a little bit that sometimes when we want to do this lambda inverse, this kind of like assume this matrix is already invertible, because otherwise the matrix, you cannot do this inverse. So we mentioned a little bit in practice, if this matrix is not invertible, what we can do, we can basically add in a little bit regularization. If this lambda matrix is no longer invertible, what we can do is we can just modify this lambda to be summation, or we can do lambda tilde, that equal to summation I from 1 to n phi I transpose, and plus a small lambda I for some small lambda. And use this lambda tilde to replace lambda in this formula. Okay. So this solution is equivalent to solve the regularized minimization problem that minimize JW plus lambda W square. So originally JW is the least square, is like the square loss. And if we add in a slightly, like a little bit lambda I here, this just becomes some regularized problem. And also you can check, in the last lecture we talked about there's a correlation, like a tabular MDP is a special case of like linear MDP. In the case you can basically check if this phi I can be only the basis vector, that is ESA. Okay, so basically you have a SA dimension and each coordinate is corresponding to one SA. If you reduce to that kind of special scenario, then this least square value iteration just becomes the standard value iteration in the tabular setting. So you can think this least square value iteration like generalized standard value iteration in the linear setting. So it not only dealing with the basis vector, but also can interpolate something like some linear combination of a basis vector, and you still give some reasonable definition for that. Yes?
Tabular MDP in general is like linear, like a subset? Or?
Tabular is a linear, is a special case of linear MDP by choosing special feature map. Yeah, we kind of like talk about that if we make this is like d-dimensional thing. If D is equal to, we can make D equal to SA, number of state times number of action. And if we choose phi SA, in the tabular case, like each state action pair corresponding to, like basically you only have like a finite number of state, finite number of action. And you can make that specific state action, the phi feature map, to be ESA. That is a basis vector in the SA coordinate as a coordinate index. and then everything goes back to the tabular setting. So tabular is a special case of linear MDP. Okay. So once we have, so now we have talking about the model that is linear MDP, also the algorithm, which is like least square value iteration. The next thing we will do for this class is we will talk about the guarantees for the algorithm. So we will start with the simplest setting we have been considered for this class, that is simulator setting. Okay. So what we want to do is we want to establish something equivalent or like some counterpart of the simulator setting for the tabular setting, but now we're doing like linear function approximation. So remember in the simulator setting, the basic strategy is basically we will query all possible SAH to the simulator. In the tabular setting, we kind of sweep over all state action and at every step, and then we obtain reward and the next states. However, now we're in this like a large space scenario. We want to do function approximation because we have like a extremely large number of states. And last time we said most of states will not even be visited once. So we may even have like infinite number of states. So in that kind of case, because we're in a large state space, it's definitely no longer feasible to query all SA. So what are we going to do instead? Ideally, we want to still be able to query some set of SA. Okay? And hopefully, the set of SA is kind of representative over the entire space. So more formally, if we have some sort of a set of SA, those are like a D different state action pair, so that phi SIAI is equal to EI or close to it. So we will later define what do we mean by close to it. Basically, the intuition is now we're in the linear space. So we somehow need to get information for all different dimensions, all different directions, and there are D different directions. If we somehow have a set of SA, like a set of a SA pair, they're representative in the sense that their feature map span the entire direction, span the entire feature space. Like in a sense, like each state action pair, the feature map is equivalent to one basis vector. So in that case, they are like a very representative over the D-dimensional space. So in this case, like we're exploiting some like linear structure in it. And query SAIAI is similar to querying ith coordinate of theta I. So, because we assume both reward and the transition are like linear in this as an inner product of some phi h and with this feature map. So in that case, if we can just query some basis vector, then we just directly knows one dimension of a theta h or something, and then we can like put them together, and we can reconstruct what is reward, what is transition, and so that we're able to learn. So we'll be more formally about what do we mean by those things. So we will actually call such a set being representative, not necessarily EI, but can be closed. We will later call it core set. Okay. So later we'll give the formal definition of what do we mean by core set K. But intuitively, you should understand this core set is something saying those set of state action pairs are like representative in D-dimensional space. They are kind of like pretty much orthogonal to each other, so that like they form a relatively good basis. So we first give the algorithm, then we give the formal definition of this core set thing, so that we can establish the guarantees. Algorithm is least square value creation with core set. So we will do two parts. Then the first part is data collection for all steps. And all the state action pair in the core set. Remember, in a tabular simulator setting, we just directly query all the state action pair. Now because it's infeasible to query all the state action pair, we only query the state action pair in the core set. So what we're going to do is we're going to query SAH and collect n samples. S1 prime till Sn prime. This part is similar to the simulator part. We just directly query the simulator and getting n samples of the next state. Again, for simplicity, we assume reward is known. And then we just put tuple this SA, Si prime into dataset D. Okay, data collection part is relatively straightforward. The only difference is now we no longer query all the state action. We just query this like core set. And next step is the value iteration part. Value iteration is always starting from the very last step to the first step. The only difference now is instead of directly doing the Bellman equation, because now it's like a function approximation, we can not directly assign to be equal because we restrict our value function to be a linear function. So in that case, we just we essentially set the value function to be the linear function that minimizes the Bellman residue. Okay. As we said earlier, SA S prime in D. Phi SA, subtract RSA, subtract VH plus 1 hat S prime. Okay. So this is like a D square. So we will set the Q value just directly equal to the linear function specified by this weight WH. And also we will set the V value similar in the tabular setting, equal to the maximization over A, the Q value. And this is good because in the last lecture we kind of also assume, although the state is infinite, action is still finite. Or you can also be infinite, but you need to assume like you can maximize this action over action A efficiently. Okay, so basically two parts. The second part is the least square value iteration. The only difference from the standard value iteration is you replace the Bellman equation by this like least square that finding the linear function that minimizes the Bellman residue instead of exactly assigning it to be the Bellman update. And then you collect the data by looking at the core set. So this is like very similar to the simulator with value iteration, but with some additional new ingredient, like the core set and the least square value iteration. So we need to understand why this algorithm is still going to work in this new setting with linear function approximation. Okay. So let's first more formally talking about what do we actually want for this core set, because we just intuitively say the core set should be something similar to basis, but this is like too vague. So by saying something is core set, we do mean core set is a set of D state action pair. Okay. And specifically, we can also denote the feature map of this core set, of the state action pair in this core set, to be psi I. Okay. Specifically, we use psi I to denote the feature map of SIAI for this SIAI in this core set. So we can essentially look at the feature map, this capital psi, that is a concatenation of the feature map of all the state action pair in this core set. Okay. So this matrix essentially fully characterizes what are the feature maps of this core set. So particularly, the core set requires the following property to hold. The first one, we require this psi to be full rank. Essentially, we require the feature map of the state action pair in this core set to span over D-dimensional space. It doesn't left out any direction. And the second important thing is we require this for any SA, any feasible state action pair. We want this psi inverse times phi SA. This is a matrix. Okay, this psi is a matrix times a vector, so it ends up with a vector. So we require this vector has a one norm upper bounded by L. And we will actually see immediately what kind of this condition implies. This essentially says you can efficiently using this set of core sets like this psi 1, psi d to to like represent any feature vector of the feature vector of any state action pair. You can think this is more like a soft version of saying this psi not only need to be full rank, but also kind of close to orthogonal so that they can represent things very well. If you have like two vectors extremely close to each other, then the representation, like using psi as a basis is like very bad in the sense that the coefficients can be very large. So I want to talk about a few things. So remark one. First, this is like, I want to talk a little bit about existence. This is a bit abstract condition of, like I say, there exists some set of SIAI. This is like the core set, and it satisfies those two conditions. You may wonder, first thing is whether this always exists. So the answer is actually yes. So given the set, this is essentially the set of all possible feature space, all possible feature vector that is supported in d-dimensional space. Then there's an algorithm finding such a core set. For some reasonable value of L. If I remember correctly, there's some like log vectors. So we omit the construction here. So the construction requires some like separation, deseparation techniques, and probably going to take another half an hour to talk about it. So we just omit here. But just first remark is it always exists, and you can even have an algorithm able to find the core set if you know the set of all possible feature vectors. The second property, the second remark I want to say is like basically intuitively why we require the second condition of the core set. It's the property 2 of core set. Implies that any feature in terms of a phi assay for arbitrary assay state action pair can be represented by linear combination of core sets with small weights. So in a sense, if we have like arbitrary phi SA, this is like the feature map for some arbitrary state action pair. So we say we want to represent it by linear combination of coset. In a sense, we want to say we want to express this as summation I from 1 to d. Let's say Wi psi I. Psi is essentially the basis given by the coset, and this is like the linear coefficients. So in the matrix expression, we can say this is equal to the psi matrix times W. Okay. W is the vector, which each coordinate is Wi, W1 to WD. So in this sense, if psi matrix is 4 rank, because we say psi is like span over d dimension, so we can resolve for W. W vector now becomes something psi inverse phi SA, which is precisely what we have here. So the property 2 of the coset directly implies the one norm of W is upper bounded by L. Yes. Any question?
Well, it seems, I guess, surprising to me that, like, if SA is much larger than D, that these can be reached by a linear combination in the first place, especially with small weights. Is that surprising, or?
It's not surprising. For example, if the feature is all in simplex, like you know, simplex is like the probability simplex, like you can generalize to d dimension. Then if the coset is like a basis, then that means all the feature vector can be represented as a linear combination, and the way one norm upper bounded by L is like very normal. So, yeah, so this is like a regularization condition. You can essentially say that. You will actually give some examples. This is like precisely what we're gonna do. The simplex feature space. So we look at the example which satisfies something like this. So in the last lecture, we talked about those simplex feature space. That is all the feature vector phi SA for SA in this set SA is a subset of, let's say, just equal to the d-dimensional simplex. D-dimensional simplex is like something x1 to xd, so that each xi is greater or equal to 0, and the summation xi is equal to 1. It's a probability simplex. So in this case, we can look at because this is like exactly the feature space, then we're saying the SIAI, the set of SIAI, D state action pair, so that they reach the basis vector equal to EI. This set gives a is like a core set. The reason is if we have the feature map of the core set, like E just equal to EI basis vector, then we know this psi matrix is identity matrix. So it first clearly satisfies the first condition, that is 4 rank. And secondly, this psi inverse phi SA, if we can check this condition, we say this is the one norm. And because we know psi is an identity matrix, so we know psi inverse is also an identity matrix, so we only need to look at the phi SA's one norm. And because all the feature map lies in the simplex, so we know that any feature norm in this simplex is equal to 1. Okay. So you can also say this is less or equal to 1. So you can say L is equal to just 1. So once we have talked about the algorithm and also the property of this like core set thing, like our linear surrogate for like the simulator thing. So now we can talk about the guarantees of such an algorithm. So theorem says if we choose m greater than some constant c times L square h fourth iota over epsilon square. It's again some like complexity. Remember this n is the number of samples we will query simulator for specific state action pair in the core set. Okay. If we query this number for each state action pair in the core set, where again this iota is some log factor. We have seen this a lot in this class. We do the log hd over p. Okay. Then, with probability greater or equal to 1 minus p, the output pi hat of LSVI, which this pi hat, we haven't defined the algorithm, but basically this, you can imagine this is like the greedy policy of Q hat. Is epsilon optimal. Okay. So it's a very similar ingredient. We just say with sufficient numbers of queries, and then we say the policy output by our algorithm is epsilon optimal. So one important thing we note is we're now in a function approximation scenario, so we're in the large state space. So as we said in the very beginning, the main motivation we want to do this new theory is now we no longer want to have any dependence on the number of state S and number of action A, so that we can get beyond the tabular setting where we require both state action and finite. We note in this theorem, this is already achieved. Like there is no dependence on the number of state and number of action. We replace it by this dimensionality, this D. Okay. So essentially, D characterizes the complexity of SA or whatever in this like linear function approximation scenario. So we can talk about the whole sample complexity. We note this n is just the number of queries we will make for each core set, each state action pair inside the core set. So we first need to times the number of steps. This is like for a single step. Then we need to times the number of state action pair within a core set. In this case, we will always make it D. Like core set always have like D state action pair. So this is the total number of sample complexity, and this is equal to some constant times h to the fifth d L square iota over epsilon square. As we said, we have no longer have any state action pair dependence. We have dimension now. Instead, we have dimension dependence, and we also have L coefficient dependence. This is like talking about how orthogonality this like core set is, like how good this core set is. So the most important thing is independent of SA. This will be the first guarantee we see that beyond the tabular setting, but later, like all the guarantee we develop for the function approximation will be of this style. Will no longer depend on SA. Yeah. What's the question?
So is this like a factor of H worse than like the value iteration we saw for generative model, like I don't know, the previous P set was like H to the fourth. Is that like factor of H a cost of using this method?
I don't remember. I think probably it's similar, but also in the linear function approximation, it can be a little bit worse. But I think it's similar.
Worse, or else like you would always use this over normal value iteration?
I think in the similar setting, it should be the same thing. So I think it should be h to the fifth as well. I think for the homeworks, we do some Princeton and some variance, so we can shave a little bit H dependency. Yeah, but I need to check it offline. That's a very good question. Okay, so now after talking about theorem, let's do the proof. So the overall proof is, again, very similar to the tabular setting with the simulator. But again, we need to do all the adjustment for this core set and linear function approximation. So we will hopefully highlight the interesting part in this proof. So the first thing we need to do is we need to write a little bit about, like reformulate a little bit, simplify a little bit about the Q-value updates. So far we're saying it's like a least square value iteration. It's doing least square. So just recall, we're saying by doing least square value iteration, WH is arg mean W summation SA S prime in the data set. And W transpose phi SA, subtract RSA, subtract the VH plus 1 hat SA, S prime square. Okay. And we note this is lambda inverse, because we already know this is like core set, so this is 4 rank, and we don't need to add any regularization. And we say this is like a lambda inverse summation I from 1 to n phi I RH SI AI plus V H plus 1 hat SI prime. Okay. Where we say this phi I, we use the notation phi to denote phi SI AI as a shortage. And this lambda matrix is equal to I from 1 to n phi transpose. Okay. This is what we have been talking about earlier in this lecture. So what we want to do is this is like a least square, but it seems a little bit different from the Bellman equation. So we need to first connect this to the Bellman equation. We do this connection by looking at the Q value, QHSA. So by definition, Q value is the linear function, which we use this weights. So Q value is equal to phi SA transpose WH hat. So this is the Q value we use in the LSVI. So we can plug it back. This is equal to phi SA transpose lambda inverse summation I from 1 to n phi I RH SI AI and plus VH plus 1 hat Si prime. Okay, so this is just plugging our solution for WH. Still, it's a little bit complicated. It doesn't look like some Bellman updates. So we need to do further simplification. We plug in the definition of linear MDP. By linear MDP, we're saying this both reward and transition are linear. So we just plug in the definition, where we first copy the first part, 1 to n, phi I. So the first part, we know the reward of SIAI is equal to phi I, which is a feature vector, transpose the theta h. Okay. This is like the definition of the reward. Let's first split the reward outside. And then we copy the second term. Transpose lambda inverse, summation I from 1 to n, phi I, v h plus 1 hat si prime. So the first term, we have a very good structure now, because we can now do this summation of phi I transpose. We know this thing by itself is lambda. So this lambda and lambda inverse cancel out. So it just becomes phi SA transpose theta h. And we know later this is equal to like RH SA. Okay. So this is very good. So now how we handle the second term. Second term, we write it in a slightly different form. We write it using the delta function. Okay. So this is like phi SA transpose, lambda inverse, summation I from 1 to n, phi I. So what we will do is we will add a direct delta function, delta S Si, delta S prime, Si prime, and V H plus 1 hat S prime, ds prime. Okay. So this is an integration over the S prime, and direct delta function is essentially only if this direct delta function, essentially you have something like an integral of delta S prime of some S tilde, S0, let's say, and f s prime ds prime equal to fs0. So you can think it's like a probability density function which put probability density, like put one probability into the specific value of s prime, s0, and everything else is 0. Okay. This is like a delta function. And here we have like n different delta function evaluated at n states we sampled here. Okay. Which is just a mathematical reformulation. So you can think this, it turns out you can make this as like a generic transition or something. So we still write in the form of p hat h vh plus 1 hat sa. But just note this p hat, this empirical estimation, becomes something a little bit complicated. Okay. So this p hat is a measure of sa. That is defined equal to, basically equal to this thing. That is equal to this phi SA transpose, lambda inverse, summation I from 1 to n, phi I, delta dot Si prime. You can think of it as some measure which essentially assign this value. We'll just write it down. You can think this p hat is a measure which assign probability mass or something. Okay. We say we have a quote we'll explain later, which assign probability mass that phi SA transpose lambda inverse phi I to the next states Si prime. Okay. Essentially, you can think this is like a summation of that kind of discrete probability. Well, the only different thing you cannot think is a proper probability because we see the probability mass, usually we require all the coefficients for probability mass to be non-negative. And this needs to be non-negative. However, in general, this phi SA transpose lambda inverse phi I can be negative. So in that sense, p hat is not a proper probability. So you can just think the form, if everything is positive, then it looks like some probability measure. But it turns out it's not necessarily true because in general, like you can think this is a negative. So it just looks like probability measure. But turns out, given this formalism, we can already like do a lot of derivation on top of it. Yes, questions?
Where do we get that phi SA transpose times lambda inverse times phi I from?
Where? Oh.
Just like, why is that?
Oh, because we can just move the summation outside. Move this.
Why do we have that? Or, oh, okay, that pH hat just comes from that.
Right, right. Okay. Yes.
You know that they're that to 1, or like that one preserved, or is that also not true?
I think it's not necessarily true. It's not necessarily adding to 1. Okay, so we have already done all the preparation work. We now like have some connections to the classical Bellman equation. We know the major difference is now our p hat has become something a bit L-defined. It still have like similar form as like empirical transition, but it's a bit L-defined that is not proper probability. It's a probability. It's just something similar to probability, but it's not probability. But still, we can still like use a lot of the previous derivation. A lot of previous derivation it still works. We just need to be a little bit more careful. So we directly use one of the previous lemma. We kind of similar to previous lemma we prove. Again, for this simulator, the most important thing is we need to look at this value difference. This is the value of optimal S1, and this is the value of LSVI computed. we kind of decompose this value into the difference in terms of the transition. Okay. And we say this is equal to summation h from 1 to capital H, pH, subtract pH hat, VH plus 1 hat, SHAH given S1. So if you still remember in a simulator setting, a tabular simulator setting, we're talking about we can decompose the value difference of the same policy but different MDP by the summation of the transition difference. This is essentially a similar lemma, but here we kind of directly jump one step. So it's not the same policy, but it's an optimal policy for each different MDP, and we use less or equal to. Okay. So the important thing is we take expectation over pi star, but here we need to do the v hat. Proof essentially follows So once we have this, we can basically focus on this arrow on this transition. So once we have this, we can look at this arrow. pH minus pH hat, VH plus 1, that's it. We always need to keep in mind this pH hat is not a proper probability anymore, so we need to be careful with it. First, we write our definition. This is equal to phi SA transpose. The first thing is this is like a standard transition probability. We know transition probability is inner product of phi and some probability measure mu. So this is equal to the inner product of phi and the integral of VH plus 1 S prime d mu S prime. The first thing, and then subtract the second thing, where second thing is we define the p hat v hat here. And that is equal to phi SA transpose lambda inverse summation I from 1 to n phi I VH plus 1 hat SI prime. So what we can do here, we can add a lambda inverse to make so that we can make difference between two terms. So we can add a lambda inverse here and times the lambda here, because this is equal to identity. And we know the lambda is equal to summation I from 1 to n phi I transpose. Okay. So we just add this identity inside here, and this is equal to phi SA transpose lambda inverse summation I from 1 to n. Little n. That's always the little. This is capital, sorry. phi I. And we say phi I transpose is integral of VH plus 1 hat S prime d mu hat S prime. And subtract this V hat H plus 1 Si prime. Yes?
Just an additional thing. Is capital N the same as D? Or?
I think, yeah, we're kind of using the notation. This capital N is equal to ND. So in every step, we're putting all the queries from different core set together. So you have ND data in this case. So for each state action pair in the core set, you have N data, and now you have D state action pair in a core set. Okay, and we note this, when we put those things together, this is actually equal to the probability of S prime given SA, given SIAI, okay, phi I, putting those two together. And by doing integral over S prime, this is like taking expectation over S prime. So we know this is actually equal to phi SA transpose, lambda inverse summation I from 1 to n phi I. We have the expectation over VH plus 1 hat S prime given SA, SIAI. Subtract one single sample out of it. So we're going back to some form which we have one random variable subtracted by its expectation, or the other way around. And we have a summation of such kind of fluctuation. So you can think, ideally at some point we're going to use the concentration inequality to fix this problem. So we note that we have n equal to little nd. We kind of already said samples per step. Which this we can further decompose this nd samples to be like n samples per feature in the core set. Times we have like d features in the core set. So this kind of tells us that this lambda matrix, which is equal to I from 1 to n, phi I transpose, is also equal to because we only query the core set, and we query each core set n times, each feature in the core set n times. So we have n copy of we query core set n times. So this j from 1 to d, and we query each feature vector, psi j transpose. Okay. We exclusively use the psi j to be the features in the core set. And we can also say this is just equal to the matrix form representation that n times psi and psi transpose. By similar manner, we can also further decompose this summation over all the data we collected for this step to be the summation over the number of features in the core set, and also the number of like basically different samples. Okay. So plug it in. We know this pH, subtract the pH hat, VH plus 1 hat as SA is equal to phi SA transpose and psi transpose inverse. Okay. We just replace this this lambda by this psi transpose. And most importantly, the later part, that is times summation j from 1 to d psi j, and the expectation of VH plus 1 hat S prime given psi j, because psi j denoted the state action pair, subtracted by 1 over n, summation L from 1 to n, VH plus 1 hat SL prime. So what we're saying is, because we know phi I are just n copy of the features in the core set, so we just directly explicitly write it out as a summation over d, and then we kind of cancel out the n factor here, and so the n becomes inside, goes to inside. It's just a reformalism by knowing this phi is just psi, but with n different copies of it. So the very good thing now is this is like the expectation subtracted by some like empirical average over, like essentially they are all starting from the same state action pair as psi j, encoded by the linear vector, and then you're getting a lot of samples of next states. So this is essentially the standard concentration, and we can say by Hofting, we call this epsilon j, and we say by Hofting's inequality, we have this epsilon j, the norm of epsilon j, to be upper bounded by some constants times horizon times iota over n. So we're almost done. We just putting everything together, and we say this is equal to phi SA transpose. We still copy the psi in transpose inverse. And the later part, once we denote this concentration part as epsilon j, we can also write it as a matrix form, which is like a psi epsilon vector, where epsilon vector, each coordinate of epsilon vector is epsilon 1 to epsilon d. And we know psi is 4 rank, so psi can be directly invertible. And so there's some part of inverse, this psi inverse cancel with this psi. And what we get eventually is become something like psi inverse phi SA transpose epsilon. And finally, by Hölder's inequality, we can say the inner product of two vector is upper bounded by one norm of one vector and infinite norm of the other vector. Typically, we do two norm, but we can also do p norm, q norm, as long as 1 plus p, or 1 over p plus 1 over q is equal to 1. And we know this by the definition of core set is upper bounded by L. And this is by the concentration inequality we already given here. So this is less or equal to C times L times H times iota, square root of iota over N. So this implies that V1 star S1 subtract V hat S1, which is we originally start with. We know we can decompose it as a summation of the transition difference, expectation of pi star, and summation h from 1 to capital H. pH, subtract pH hat. VH plus 1 hat, SH, AH, given S1. We already know each term is upper bounded by this, so we only have a summation H left. So we know this is less or equal to C times 1 further H factor times everything here. So times L times H squared, and square root of iota over N. Finally, recall that our choice of N that is greater than some constants times L squared H to the 4th iota over epsilon squared. By choosing N equal to this, we can guarantee this is less or equal to epsilon over 2. Okay. And similar to simulator setting, this is like 1/2 of it, and the other half is mostly the same, so with the details. Basically, similarly, you can also prove that VH V1 hat S1 subtract V1 pi hat S1. This is again, you can decompose it as a difference in the transition and then do the same argument, essentially is the same argument. And you can also say this is less or equal to C times L H squared square root iota over N, which is again epsilon over 2. Okay, and this finished the proof. Yes?
Just making sure, what's the actual final difference we're looking for when we add those two together? It's like V1 star.
Yeah, we're looking at the difference of V1 star S1 subtracted V1 pi hat S1. This is what we want to prove is epsilon optimal. So each part is epsilon over 2, so when you sum them together, it's just epsilon.
Wait, so just making sure this only applies for linear MDPs, right?
This only applies for linear MDP, yes.
That's a lot of MDPs. And I guess, at what part do we use, or do we have to worry about the fact that the p hat is different than a normal p hat?
I think it's also, especially when we do the decomposition like this, if you still remember in the previous lecture, we kind of say there is some symmetric decomposition. Instead of having pi star here, we can also, this is p pi star. We can also do p hat pi hat pi star, and we have a v here. But that is no longer feasible because p hat is no longer a transition. So now we can only do one proper decomposition. Yeah. So whenever we need to use something summation to 1 and it's a probability, we need to be very careful. And unfortunately, in this proof, we don't use that.
And is it like the other one where if you were to somehow use some clever Bernstein's thing, then
you can possibly shave a factor of H. Although in the linear part, the Bernstein is a lot is a bit more difficult. I think this one you can still do, yeah. But later, like when we do the optimism stuff, the Princeton is a lot more involved. Okay. I think that basically finished what I want to talk about for the simulator setting. I think today there are some calculations, but basically I hope you can like have some taste of some sort of like a function approximation, how to make it work. Like basically you can see the connection between this and tabular setting. And later part of our function approximation, we will talk more about the algorithm, formalism, and guarantees, and less about the proof, just because it's quite involved. Okay. I still hope you can like get some spirit from this like linear kind of proof. Yeah, later on it's kind of more complicated. So starting from the next week, we will talk. We'll first finish the linear part by talking about in the online setting how we do the optimism, and also whether we can like relax the linear MDP assumption we said that in last lecture. It's like a very strong assumption. It's very restrictive, only apply to like tabular MDP, and certain like simplex kind of feature has some restrictions. How we're gonna generalize that by using some new idea instead of the standard optimism, but we kind of change it to like the global optimism, and then we kind of generalize those ideas to the general function approximation scenario beyond linear setting. Okay, see you next week then.